loop amplitudes. We're mostly going to focus on one loop today. So there are several things that we need to understand. We need to, first of all, generalize the color decomposition. The thing that's, of course, different about loop amplitudes compared to tree amplitudes is now we actually have Feynman integrals that will appear in the answer. So we need to understand what Feynman integrals can appear. And I think we're going to spend most of today on that and then part of tomorrow as well. Maybe I should write what Feynman integrals can appear. And then finally understand how to compute the coefficients of these integrals. So I'm not going to do a detailed derivation, and not that I did a very detailed derivation of the tree level ones, but at least I gave you the ingredients to derive it yourself. I'm not going to do that here, although I encourage you to think out the color structures that would arise from thinking about sewing things where there are now loops in addition to trees. So here at one loop, we're going to have a single trace. So at tree level, we had just single trace color structures. And at one loop, we'll again have those same single trace ones, except that they will be multiplied by a factor of n, the number of colors. And again, I'm talking here about pure gluon amplitudes. All these things have some modifications if there's matter fields that transform in, for example, the fundamental representation or really anything other than the adjoint. We also get double trace structures at one loop. Oops. And this color structure is called the leading color structure. The others are called subleading color structures. And when we put this all together and we write down an expression for the one loop amplitude, then again, we're going to have a dependence on the external spinors, and of course on the external helicities and on the color indices. That's the same as at tree level. So at tree level, even if our theory contains matter fields, then the internal lines have to be gluons if all the external legs are gluons. Here, if the theory does contain other matter fields, even if all the external legs are gluons, there can still be, of course, other particles circulating around in the loop, so we have to sum over the kinds of particles that can circulate in the loops. For everything I'm going to talk about today, I'm still going to assume we're in pure Yang mills, so in fact those particle types are just the gluons themselves, and then of course if it's other than the gluons, there can be some number of families, some number of multiplets. Then we have a sum over color structures, which I'm going to label by C, and those go from 1 up to the floor of n minus 2 plus 1. Then there's going to be, again, a sum over permutations. And here I'm going to have to explain what is meant by this notation after I've finished writing out the formula, because that's not a standard thing you can look up in the math books. So we have generically double traces. And in the case that C is equal to 1, the first trace is empty, and so you should think of that as being the trace of the identity matrix, which gives you a factor of n for the single trace contribution. And this then is multiplied by the kinematic factor, which in general depends on the type of particle circulating around inside the loop, in addition to the number of external gluons. It also depends on the color structure. And again, in the usual notation, I'm going to write the helicities as a superscript. So Sn is all the permutations of n symbols. So we start out with all possible permutations of the n legs, but then S and C here, we have to divide out by all the permutations that leave the traces invariant. So that would mean cyclically rotating one of the traces, cyclically rotating the other one, exchanging the order in one of them or in the other one. That can carry some signs. And finally, if the two traces happen to be equal length, so let's imagine that we're looking at the 6-point amplitude and we're looking at C equals 2, so the C equals 3, the 3 trace and the 3 trace, the SNC will also include a term that exchanges the two traces. And the corresponding color-ordered amplitudes have to have the same symmetries of the SNC, just as at tree level, except that the structure now is a little bit more complicated. So the C equals 1 term is called, it's the coefficient of the single trace, which I said is called the leading color. So that's the leading color. Yes? You can do both of them together in SUN still. That will just introduce a sign, right? Just like at tree level. So there's still a reflection identity. So this is the C equals 1 is the leading color amplitude. And it's called that partially because of the factor of n, so it dominates in, for example, differential cross-sections over the subleading color amplitudes, but also because of the way that the color sums work. If you square an amplitude and then sum over all colors, the contributions, the C equals 1 contribution will end up with a larger power of n compared to those coming from C greater than 1. So these are called subleading color. And they're suppressed by powers of n, and as it turns out, they're also, in many practical applications, even less important in differential cross-sections than you might expect just from the n counting. But if you're going to do precision physics, you still may need to calculate them. You just might not need to calculate them to the same precision as the leading color contributions. The other thing that's very special at one loop is that these subleading color amplitudes, it turns out, can be written as some over a special set of permutations. I'm not going to explain this in more detail over the leading color contributions. So once we've computed the leading color contributions, then just by doing algebra, we get the subleading color contributions for free. And that's very special to one loop. Beyond one loop, you really need to calculate these things independently. So at two loops, I think you can probably guess what's going to happen. The basic structure is that of three traces. So we would have, I'm not going to write out the T matrices here, but they're inside the traces. And sometimes one of the traces can be absent, and so we're going to get a two-trace structure with a power of n. And finally, we can get a single trace structure with two powers of n. But that's actually not the whole story. There's one more novelty at two loops, which is that there are still going to be subleading color structures with just a single trace. And these are related to the existence of oriented surfaces with boundary. In this case, it's an oriented surface with two holes and just a single boundary. And that's your first exercise for today, is draw this surface. And these, beyond two loops, there's not really any other novelties. There's, of course, more traces, and there can be additional kinds of subleading colors with fewer powers of n than you might have naively expected, but otherwise there are no new features. So that's what we need to know about the color structure. And now we have to think about doing what I've called before a Gedanken calculation. And I realize it's, from discussions with some of you, it's not a term you're familiar with, but it means just imagining doing the calculation in your head without actually doing the calculation explicitly. So we imagine doing a calculation with Feynman diagrams. And the virtue of Gedanken calculations is that even for cases where you'd have to write down 10 to the 21 actual diagrams, you can just imagine that you've written them all down because you're not actually doing it explicitly. So we know how, in principle, to calculate a one-loop amplitude or even a color-ordered one-loop amplitude. We just do the color-ordered diagrams. And we write down for some endpoint process, we write down all the Feynman diagrams, and now we start to think about what integrals are there. So even in cases where the number of diagrams is well shy of 10 to the 15 or 10 to the 21 that we saw appearing during the colloquium, it still would be a huge amount of work because, first of all, just as at tree level, there's going to be a gauge containing information that ultimately will cancel out, but also because there are going to be a lot of the work, if you imagine, write down one Feynman diagram, write down the corresponding integral, do the integral, move on to the next diagram, so on and so forth. There's going to be a huge amount of repeated work because many of the integrals are going to resemble each other. And that's reflected in the fact that we have linear relations between Feynman integrals. And we're going to see one class of relations today, and we'll look at another class tomorrow. And when we have the choice between just kind of doing all the integrals or trying to find linear relations between different integrals, and this is true not just for Feynman integrals, but more generally in life, then we should remember that analysis, like integration, is hard. And hard means computationally expensive. Whereas algebra is easy. And that means that it's computationally cheap. And what that means in practice is that you can go to much bigger problems. So if you turn analysis into algebra, you can tackle much more complicated problems than you would have been able to do otherwise, and that's why it's really interesting. So if we can take advantage of all the linear identities, then we can hope to get down to what's called a basis or a set of master integrals. And these integrals, because there's no more algebraic relations between them, there's something about them, there's analytic structure about them that's distinct. And that means that, roughly speaking, their coefficients can't really mix under gauge transformations. So the coefficients of each of these master integrals is going to be gauge independent, and that in turn is going to mean that you're going to be able to find compact representations for those coefficients. So again, as I've said before, we're getting rid of Feynman diagrams except for thought experiments or thought calculations, but the integrals are still with us, and so we need to start writing them down. I expect this is an integral you've seen in your QFT course, but if not, that's okay. So I'm going to write down for, I've already actually introduced the notation, so let me use it. So we have four propagators, four denominators, and right now we'll just stick a 1 in the numerator again, just as a reminder. Here K12 is just the sum of K1 and K2. So as long as all the external momenta are massive, then this integral is well defined, but we want to start thinking first about the massless case. So we want to actually consider, well, beginning the case where all the ki squared are equal to 0, and then later where some of them are equal to 0 and others are not 0. And when we do that, then those of you who already have done some calculations know that this expression makes no sense because it's full of divergences. And so we have to go to dimensional regularization. We have to do our loop integrals in 4 minus 2 epsilon dimensions instead of 4 dimensions in order to regulate those divergences at intermediate stages of a calculation. Now let's see, how many people here have seen dimensional regularization in their field theory course? I think it's essentially everybody. Good. So just as a reminder, so first of all, I'm going to leave the I epsilons implicit going forward. They're always really there, even if I don't write them down. So there's really several different roles that dimensional regularization is playing. One of them is which is more of interest to us here, is that it's regulating the infrared divergences. And for that purpose, we should take, so we have d equals 4 minus 2 epsilon by convention for the definition of epsilon. So then we want epsilon less than 0 to regulate IR divergences. On the other hand, to regulate UV divergences, we really want epsilon bigger than 0. And so really you should be thinking epsilon either as a formal parameter or really off in the complex plane somewhere. And that's how you should think of these integrals as being defined. So in general, the ultraviolet divergences we're going to absorb into the definition of the coupling. In fact, their appearance is anyway just a result of the hubris of assuming we could define the coupling at arbitrarily small distances, arbitrarily high energies. But for infrared divergences, it's much more subtle, and we have to typically carry that regulator with us all the way to a physical observable, which might mean some physical cross-section with experimental definitions of what's observed. So in particular, the one-loop amplitudes, you can easily define a version of them that is UV finite, but they are going to remain infrared divergent. The amplitudes themselves are not physically observable. It's only when you finally combine them with other contributions that you can hope to get something finite. So one thing, when you were taught dimensional regularization, I don't know if you were actually taught about it in the context of spinning particles, but one thing that's better to do than what's traditionally done in the textbooks is that the external momenta and polarization vectors the traditional way of doing it would be to continue them into d dimensions as well. These we're going to leave in 4 dimensions. So they will have exactly 4 components, both the polarization vectors and the momenta. And we'll see actually in probably about 20 minutes how that helps simplify the structure of our calculation. So it's not a Feynman diagram, it's just a diagrammatic representation of an integral. Again, the convention is that we have the momenta directed outwards. That's what the arrows mean. We can think at this point, everything here is a scalar line. There are no indices. And I'll put the loop momentum in over there. So when we're writing down our endpoint amplitude, then of course the most complicated graphs are all going to have 3-point vertices in terms of Feynman vertices, and the loop is going to go through all of them, and maybe there's a loop momentum at each vertex. There could also be an external momentum. So the most complicated integral that we're going to have to consider is of this form. I should have actually changed this as well. So now we're going to have the same denominator, same type of denominators here, except we're going to have n propagators instead of just 4. And in addition, we might have powers of the loop momentum in Yang-Mills up to n. If we were doing gravity, then we could have up to 2n, because we can have 2 momenta at every vertex. But in fact, this first phase of reduction doesn't really care about the number. Now, these are called tensor integrals, and the traditional way of thinking about it was to deal with them as tensors, but that in fact doesn't really make a lot of sense, because these loop momenta are dotted into external vectors, which I'm going to write here just as Vj. So the way this term will actually appear will be L dot V1, L dot V2, and so on and so forth, L dot Vn. These external vectors, in our case, are going to be either momenta or polarization vectors. If the theory contains external, or if the amplitude contains external fermions, they might be spinor strings as well. So even after it's contracted, because of the powers of the loop momentum in the numerator, I'm going to abuse language a little bit and continue to call it a tensor integral. So the first thing we can do is take advantage of the fact that these V's are strictly in 4 dimensions. We can choose a basis of 4 external momenta, for example, K1 through 4. And for the moment, let's assume here that n is bigger than 4. And we can now expand any external vector in terms of some set of coefficients, which I'll call omega here. So these are still vectors. And there's a very easy way to compute these coefficients, which some of you probably already know. And that's to make use of an object called the Graham determinant. So the general form, it's a function of 2 lists of momenta, here called Q, P, and Q. And it's the determinant of the matrix of dot products of these sequences of momenta. The factor of 2 here is for convenience. Not all definitions in the literature follow that. And in the case where there's just where P's and Q's are the same, then conventionally we'll write it just as a function of a single list of arguments. So how many people are already familiar with Graham determinants? Okay. Now, Graham determinants are useful because they vanish if any of the P's are actually linearly dependent. So for example, if one of them is proportional to another one, likewise, if any of the q are linearly dependent, again, it'll vanish. And the thing that's really worth keeping in mind here is this vanishing is not identical. You don't just compute the object and find that it's 0. If you were to compute it for 4-dimensional momenta, then you'd find numerically it's 0. It's a non-trivial vanishing. It's a result on the invariance. Let's say if you're taking all external invariance, that is non-trivial. It's something that is implicit in the way that the dimensionality is constraining different momenta. So you can, likewise, if you differentiate with respect to one of the momenta here, then you can define a gram determinant, for example, with an index free. So if I differentiate with respect to the third p, then I would get an object which you can think of as a dual vector. And then you can write down equations for the omegas by contracting it with these dual vectors, and it's usually convenient to normalize them by the gram determinant of your basis. So that means that here we can expand, let's say, the first external vector in terms of our set of basis. And so without any loss of generality, we might as well assume that V is one of these basis vectors. So we now have to think about, we have one factor in the numerator, which is the form L dot some kj, maybe 1 through 4, maybe you've chosen some other set, doesn't really matter. And this dot product you can write as a difference of two denominators. So it's the kj here lies in between two different denominators. So you'll take the difference of those denominators, and then possibly you have to add back in some external invariant. So for example, if we have L dot K2, then we can write that as 1/2 times L minus K1 squared minus L minus K12 squared plus S12. So if we write out the dot product in this form, then what happens here? Well, we started out with L vectors, and here we lose one vector and we lose one denominator. Likewise, we lose one power of L in the numerator and we lose one denominator. Here we don't lose any denominators, but we do lose a power of the loop momentum. So that means that this is a partial fractioning identity, and it takes an endpoint rank n. So the rank is just the number of loop momenta in the numerator. And it writes it integral, and it writes it as an n-1 point. Or more generally, if we'd started not with rank n, but some rank j, we could have had fewer loop momenta than maximal. Then we would write it as a linear combination of n-1 point rank j-1 and n point rank j-1 integrals. And we can now repeat this process. So of course, the external momenta for the n-1 point integrals are different, because one of the external momenta now will be a sum of two of the initial external momenta, so it'll be massive. So ultimately, even if we're doing fully massless amplitudes, we're interested in integrals that have a combination of external massless and massive legs. And in particular, the basis set of momenta then may have to change. There's nothing incidentally wrong with choosing massive momenta to be in this basis. It doesn't change anything. You can always express a given external vector in terms of them. So if we iterate this procedure, then ultimately we'll get down to what I'm going to call scalar integrals. That is, integrals that have no powers of the loop momentum in the numerator. And these scalar integrals can go up to endpoint ones. And we're going to get tensor integrals in this modified sense of you still contract the loop momenta into external vectors with up to 4 external legs. When I have 4 external legs, then I don't have 4 independent momenta to use as a basis anymore, so at least this version of the reduction no longer works. So let's think a little bit about the scalar integrals. And this is an example of something that would not be possible if we continued to take the external momenta in d dimensions. We can write down a gram determinant. So let's write down the following determinant. Again, the numbers here are just represent the momenta with the same indices, so 2 represents K2. It's not literally the numbers 1 through 5. So let's think about, for example, the 6-point integral. So these momenta are all independent in the sense that there's no additional relation with them except for the one that's given by the fact that they all lie in 4 dimensions. So this object, if the loop momentum were 4-dimensional, it would obviously vanish, but it vanishes non-trivially. And that isn't altered by the fact that we take the loop momentum to be d-dimensional. So the fact that it's d-dimensional means that the vectors in the first row are now linearly independent, but that's not true for those in the second row. So this object still vanishes. And if we introduce a little bit of notation, where this bracket notation with some function of the loop momentum, meaning the one loop integral where that polynomial is inserted in the numerator and the denominator is the same as a generic endpoint integral. Then we should consider the 6-point integral with this G1 polynomial inserted in the numerator. So, well, let's see. The polynomial itself vanishes, so the loop momentum will vanish too. But because the polynomial vanishes non-trivially, the loop integral will vanish non-trivially too. And what we want to do is go through the reduction arguments on this integral. And we can now express it in terms of denominators, 1 factor of denominator per term, and external invariance. Whoops. Meters. And so the terms where we extract some denominator will ultimately give us 5-point integrals. And there's also going to be a term that has no powers of loop momenta at all after you've re-expressed it in terms of denominators. That's the analog of the external invariant term. And of course, if we just have something that's independent of the loop momentum here, we just pull it out front and we're just left with the scalar integral. So when all the dust settles, that's going to give us an equation of the form 0 is equal to some coefficient. And you need to check that that coefficient is non-zero, but you can do that numerically, for example. Plus some sum with various coefficients times various 5-point integrals. So that says that thanks to taking the external momenta to be strictly 4-dimensional, we can actually reduce the scalar 6-point integral. And you can repeat this argument for any n that is greater than 6 as well. So that leaves us with the, if we go back to our list here, we have not just, we don't need to think about up to n-point anymore. We just need to think about scalar integrals up to the 5-point integral. Now, in the 5-point case, of course, this Graham determinant does vanish trivially because K5 is just the sum of these 4 momenta, so we can substitute that back in. And if you literally have a repeated momentum, then of course the determinant will have 2 rows or 2 columns that are proportional, and then it will vanish identically. So we can't use this in the 5-point case. What we can do in the 5-point case is to consider another Graham determinant, G2. And now we'll take both of the rows to be the same. So this thing is not 0. But it is very special because if I were to take the dimension to actually go to 4, so if the loop momentum were actually 4-dimensional, then this thing would vanish. So there's a certain heuristic sense in which you can think of G2 as being of order epsilon. Because remember, the components of L that are outside 4 dimensions are really just 2 minus 2 epsilon dimensional. You can actually make that precise, and the other analysis that would take much too long to go through also shows that this particular numerator also cancels off all the infrared divergences if you were to take d to 4. So if you put that in the numerator, in spite of the fact that naively you might think they're infrared divergences, in fact, they're all gone. And so it turns out that this integral is literally of order epsilon. In fact, this integral is proportional to the 6-dimensional 5-point integral, but that's not really that important here. So we can, again, we can expand G, write it as a sum of terms with some denominator plus a term that has no dependence on L. And that then tells us that we have a decomposition of the scalar pentagon 5-point integral in terms of some sum with coefficients of 4-point integrals with different denominators from the original 5-point integral missing, plus some coefficient times the 5-point integral with the G2 inserted. Now, as long as we're interested in an NLO calculations, one order beyond the lowest, then these terms will never contribute to a physical observable. This thing is going to be of order epsilon, and so we can just drop it. And that means that for purposes of an NLO calculation, we can exchange a scalar pentagon for a set of box integrals. I'm sorry, why the? So again, this is some polynomial in the loop momentum. And I'm going to write it out in the same style as it's going to be a denominator times something plus another denominator times something plus something that has no dependence on L. And then the thing that has no dependence on L will turn into this. The things where their denominators will cancel one of the denominators and turn into the boxes. And then, of course, the initial equation had the G2 integral, which I'm just keeping here. So that we can now pull this down to just 4-point integrals. And now we can use a technique which most people these days call Passarino-Veltman. How many people have heard the words Passarino-Veltman in your? Okay, so let's do an intellectual honesty check on your professors. How many people have heard this described as Brown-Feynman? So the original idea of using Lorentz invariance, so we're going to use Lorentz invariance and parity to show, for example, that, or to observe that if you have, for example, a single power of the loop momentum in a box integral, then we're going to have a sum over some coefficients times the possible vectors that can show up, independent vectors, which here I'm taking to be 1, 2, and 4. And each of these coefficients is then going to be proportional to the scalar box integral. And so Passarino and Veltman worked this out in great detail along with formulas for the boxes, but the original idea of doing this is in a paper from Brown and Feynman sometime in the 1950s. And like most of Feynman's papers, it reads like a modern, almost modern paper, not because he was so forward-looking, but just he influenced the way we write papers to this very day. So using that, we can then eliminate all of the boxes and also triangles and bubbles that have numerators. And ultimately, this lets us reduce things to a combination of boxes, triangles, and bubble integrals. So the external lines here could be either massless or massive. They're going to be, in general, sums of the original external momenta. And one thing that I haven't actually discussed here is that this same reduction can also give rise to rational terms, terms that have no Feynman integral at all. And these things, in a sense, arise from epsilon over epsilon type terms. Incidentally, this kind of numerator is called an evanescent numerator. And if you combine evanescent numerators with ultraviolet divergences, you can get epsilon over epsilons, and those things will give rise to rational terms. They actually have non-trivial analytic structure like logarithms if you go to higher orders in epsilon. So if we now denote massive legs by double lines, then we get a whole variety of different box integrals. So this one is not too surprisingly called the one mass. This one is called where the two masses are adjacent, is called the hard two mass box. And the one where they're diagonally opposite is called the easy two mass box. And then there's only one kind of three mass box, and of course only one kind of four mass box. The four mass box is actually dual conformal invariant, which is then responsible for the fact you can express it in terms of smaller number of variables than you might naively have thought. And there are three different kinds of triangles. We can get one mass triangles, two mass triangles, and three mass triangles. And of course, there's also bubble integrals. So at one loop, the most general amplitude can be written in terms of integrals of this form, where of course the external legs are sums of the original momenta. So that also tells you that rather than having to do many, many different kinds of integrals, there's actually only 9, or maybe I should say 10 if you include the massless box, different integral functions that you need to calculate it. And most of these are simple enough that just coming out of a first field theory course, you can do them. This one, at least to do by traditional means, is a little bit more involved and was actually the subject of a research paper in my lifetime. So that tells us that we can write an amplitude. So this is our basis of integrals. We can write an integral, an amplitude, in terms of a basis and possibly some rational terms. We're not going to talk any more about the rational terms today, or actually in this lecture series, but these coefficients and the rational terms, they're all rational functions of our spinor variables. And of course, that function has to be also a function of the spinor products because it's because of Lorentz invariance. So this is actually enough at one loop. At two loops, there are additional concepts which we need to learn about and some additional technology, which we'll come back to tomorrow. So let's see how we can go about calculating these coefficients directly. And that's where we come to the unitarity method. So unitarity is just the observation that of course, at its simplest form, that the S matrix conserves probability. And you can translate that into the observation or the equation that the discontinuity of a one-loop integral can be written as the phase space integral of a product of two tree objects. So this would be, for example, the discontinuity in the I through j channel. Well, really write this as the argument. And what this amounts to doing is replacing two propagator denominators, or replacing two propagators by delta functions, putting these lines on shell. And the basic idea of applying a unitarity method to this equation, which is often called the master equation, is to apply it on both sides. The discontinuity of the integral function is something that you can compute explicitly, and the discontinuity of the amplitude is then something you're going to be able to write in terms of tree amplitudes, and that will give you a set of equations for these coefficients Cj. So in the simplest form, then we would insist on having two specified propagators, and there'd be some number of integrals that would have them on the right-hand side. And on the left-hand side, we would get the discontinuity of the amplitude, which we can express as a phase space integral over tree amplitudes. But in fact, and then of course there'll be some integrals that lack one or both of the specified propagators, and they will simply drop out of the equation. And then one would iterate over all choices of pairs to get enough equations to be able to isolate the Cj, to be able to solve for the Cj's. But one can in fact go beyond that and insist on the presence of more than two propagators. So for example, we could insist on looking at contributions that have three specified propagators. And among other things, you can see right away that that's going to make the bubbles drop out because they only have two propagators. So it's going to simplify the structure of equations. So we can insist on three propagators. In fact, we can go beyond that, and we can insist on four propagators. And that's the most that you can do through order epsilon at one loop, because we don't have any integrals that have more than four propagators. So if we insist on the presence of four propagators, that's called a quadruple cut. And the nice thing about quadruple cuts is that they're going to pick out a specific box integral on the right-hand side, because all the other boxes will lack that particular configuration of propagators. And then, of course, the triangles and bubbles won't have those four propagators, and so they'll just drop out. So if we do a quadruple cut, then we'll be able to isolate a single coefficient j, and that I'm going to go through explicitly. Having done all the quadruple cuts, one can then relax them to look at triple cuts. You already know all the coefficients from the boxes that would arise, and then you can isolate one triangle at a time. It turns out that to do the bubble integral is a little bit more subtle, but you can apply the same logic and ultimately extract its coefficient as well. Now, the other thing that isn't maybe completely obvious, but turns out to be true for the quadruple cuts, is we can actually work in 4 dimensions. In a sense, the relevant analytic structure. So now we're not so much talking about discontinuities, we're talking about the structure of the integrand, and we'll understand maybe towards the end or maybe at the beginning of tomorrow's lecture, we'll understand what more specifically I mean by when I say analytic structure. But we don't need to worry about the epsilon terms for the coefficients of the boxes. So let's start with the right-hand side, and there's some integral where we're going to take the quadruple cut of a box integral, and again, I'm going to just write it out in terms of 4 dimensions in anticipation of taking that cut. So now some of the legs are going to be massive. I'm not going to specify exactly which one right now. That depends, of course, on the integral in question. So if we're just following the Kutkusky rules, which I'm not going to have time to discuss, but those are the ones that tell you that to take the discontinuity, you replace the 2 propagators that surround the channel in question with a positive energy delta function. So this integral is going to go to d4L, L squared, delta plus of L minus K1 squared, delta plus of L minus K12 squared, delta plus of L plus K4 squared. And the plus here is just saying that we're choosing the positive energy solution. So here it would amount to saying that it's multiplied by theta of L0, and similarly for the other delta functions. So, well, this is a very fancy thing to write down, but really what it's telling us to do is that we have to solve the simultaneous equations, L squared equals 0, L minus K squared, K1 squared equals 0, L minus K1 minus K2 squared equals 0, and L plus K4 squared equals 0. So in general, the number of solutions to equations beyond linear in multiple variables is a very complicated question. But here we can actually take linear combinations. There's just an L squared in each of these equations, which we can get rid of. It says that L dot K1 also has to vanish, and also L dot K2 has to be equal to S12 over 2. And finally, L dot K4 also has to vanish. So now we have 1 quadratic equation and 3 linear ones, and you might hazard a guess that we should expect 2 solutions. And in general, that would be a very risky guess, but here it turns out to be correct. There are, in fact, 2 solutions. So let's go and find those solutions. So let's assume for right now that both K1 and K4 are massless. We'll make no assumption about K2 and K3. So this equation tells us, first of all, tells us that L has to be an on-shell vector. So we can write it a massless on-shell vector, so we can write it as the outer product of 2 spinners. This equation tells us that one of those spinners should be a spinner associated with K1, so that way we can get it to be collinear with K1. And this equation says that one of the spinners should be one of the K4 spinners, so we can get it to be collinear with K4. So one possibility is to write down, get the normalization right, something that's proportional to an angle 1 and a bracket 4. So that's, by the Fiertz identity, that's going to solve the first equation, and of course it clearly also solves the second and the fourth equation. If you dot it into K1 or K4, you're either going to get the angle product of 1 with itself or the bracket product with 4 from itself, and that's going to vanish. So we have one more equation, which is this equation, and we have one more free parameters, so we can impose that equation and solve it to find that Xi is equal to S12 divided by the spinor string 1, 2, 4. Now I could have started with angle 4 mu bracket 1 just as well, and there is indeed another solution which has the form 4 mu 1 and Xi prime is now equal to S12 over 4 to 1. You can do a quick sanity check to see that this solution for L has no spinor weight in either 1 or 2, and of course not in 2 either, and that's what it should be. The loop momentum, the solution of the loop momentum shouldn't be carrying any spinor weight with respect to the external momenta. So, does anyone see a problem with what I've written down? Yeah, of course you do. That's cheating. Okay. So these solutions are in general complex. This is a complex vector, and that's a complex vector. But our delta functions are real. So they're looking for real solutions. In fact, it's not even clear what this positive energy condition is supposed to mean if the loop momentum, if the solution here is complex. Now, there's nothing wrong with that. You could plug them in here, and then the equation you would get on both sides of the master equation is simply 0 equals 0. So we haven't actually violated any norms of arithmetic, but we also have not gotten a useful equation. So in order to solve this problem, we need to redefine what we mean by a cutting, essentially redefine what we mean by these delta functions. And the way we do that is that we should think of cutting as changing contours, changing integration contours. So a loop integral, it's implicitly, there's of course I epsilons here, so there's kind of little deformations of the contour into the complex plane, but we're working on something that's defined along the R4 slice inside C4. So there's 4 components, and so it's really lying inside a 4-dimensional complex space. And so we're going to change that contour to some other contour. This is not a contour deformation in the usual sense where we have some integral in the complex plane and we shift the contour as long as we're not crossing a branch cut or a pole or something like that, and we leave the integral unchanged. Here we're going to change the contour, and we're essentially going to extract a residue. So let's consider a polynomial, let me call it poly 2, as a function of z, and let's assume that it has a simple root at z0, and its value at z0 is equal to a. So we can write down a single-dimensional contour integral, which is very similar in spirit to a delta function. So we have some numerator polynomial, and then we write down our chosen polynomial in the denominator. And our contour of integration here is going to be a small circle that surrounds z0. Now, I assume that your complex analysis course is not so far in the past that you can't do this integral. But what you'll find when you do it is that you get the following expression. So you'll get the derivative of this denominator polynomial evaluated at z0, and you'll get the numerator polynomial evaluated at z0. This is the result of it. So this is very similar to what would happen if you had a delta function whose argument was poly 2 minus a. The big difference is that there's no absolute value here. It's just the polynomial itself. So for the purposes of cutting, we're going to define what we mean by a delta function. So it's a generalized delta function. So we have some integral. This really you should be thinking of as an integral over some component of a loop momentum. And then we're going to define this integral to be just this contour integral that we've just written down. The one that I've written down over here. Now, of course, there's no problem with having A here be complex. Everything is fine. We get a non-trivial answer. And it's precisely this sense in which the different integrals have a different analytic structure. They have different locations of their poles off in the complex plane. And here the residues are simple, but in more complicated situations, you might have integrals that have overlapping poles but different residues. So again, in the one-dimensional case, we have maybe start out with some integral. You might think of this maybe as the integral along the L0 component. I really should use a different colored chalk. So our original contour is over here, and we're going to replace it. So there's some poles off in the complex plane. We're going to replace it by poles surrounding them. And again, to emphasize, this is not a deformation. It is not supposed to leave the integral invariant. In fact, it's extracting kind of some intrinsic residue of the integral. And we're going to, so this is still all on the right-hand side of the master equation. We haven't gotten to the left-hand side yet. So these solutions are called global poles. And extracting these residues in general in multivariate situations requires use of computational algebraic geometry tools. But here, and in certain number of other even higher loop integrals, it's simple enough. We just have 4 independent degrees of freedom, and our contours are just the products of circles around them. So they're really just 4 tori. So there's a circle across a circle, across a circle, across a circle here. Okay, so we have 2 contours, 2 global poles, and the question is, which combination of these contours should we take? I mean, the simple, naive guess would be you should weight them equally. I mean, you have no other choice, but how do we choose? And so that's one question. And there's another puzzle, which is not so obvious. But when we did our tensor reductions, when we did the Brown-Feynman Passerino-Veltman procedure, then we implicitly relied on the fact that integrals of this form actually vanish. So this thing is a Levi-Civita tensor. I assume all of you know what that is. So that's where we made the assumption of parity, that the integral was parity symmetric. On the other hand, depending on how we weight these contours, we might actually break that result. So for example, maybe we're actually supposed to take the difference of these two contours, and that so the amazing thing is that these two problems cancel each other out. So if we insist on this equation at the level of the cut, then we find the condition, I won't work it out for you, we find indeed the condition that if you were to take arbitrary weights of the two circles, then insisting that the cut of this equation maintain the 0 on the right-hand side would in fact say that the two weights have to be the same. And of course, exactly what the weight is doesn't really matter because it's going to cancel out on both sides of the master equation. So I think we will write out the quadruple cut today, and then I will do the example at the beginning of tomorrow's lecture. So the right-hand side is very simple because it's just a box integral. We have, of course, some coefficient. This is the unknown coefficient we're trying to solve. There's some Jacobian from doing the contour integrals. It's the analog of this, the derivative of poly 2. And then we, of course, are now summing with equal weight over the two solutions, so we have to count those solutions. What about the left-hand side? Well, the left-hand side says find a place in the amplitude. So again, if we were thinking about some Gedanken calculation, we've written down all the Feynman diagrams. We find the 4 places corresponding to the propagators that we're isolating. And we remove those propagators. We set those lines on shell. If the propagator is missing in the diagram in question, while you can multiply numerator and denominator, you can remove it, but then the factor of the denominator and the numerator will just give you 0. So that will drop out. So what we're going to end up with is, on the left-hand side, is precisely a product of tree amplitudes where we've set the intermediate legs on shell, and because we have a quadruple cut, there's 4 different objects, which I'll label A with great, I suppose in some set of lectures I should choose names and call them like, I don't know, Alice, Bob, Charlie, and Donald or something like that. But physicists are generally not very inventive in their naming, and I suppose I'm not any different. And of course, we're going to have to sum over the helicities of each of these contributions. We have to sum over all the different types of particles that are going around the loop. So we're going to sum over both of the solutions. The amplitudes here can be different at the different poles. We're going to sum over the species if we have in addition to gluons, maybe fermions. And even in the case where we just have gluons, we have to sum over the helicities going around the loop. And then we're going to have the product of the 4 amplitudes. These are now tree amplitudes because we only had one loop and we broke it. And of course, when we, for example, weight the contour and whatever the Jacobian is, it's going to appear here as well. So of course, when we set the two equal, that Jacobian will cancel out, and our final formula will just be this expression times 1/2. That 1/2 from counting the number of solutions. So let me just finish for today. I don't know why I've ended up going much more slowly, but maybe I'm tired too, the way the audience looks to be at this stage of the day as well. So this expression is purely in terms of on-shell. Wow, that's really a thin chalk. The camera probably won't like that. Let's try this one. Expression in terms of on-shell. Come back. I don't know how far the camera goes, so I'll stick to this part of the board. Tree amplitudes, but of course with complex momenta. And the complex momenta are crucial. Again, just as they were in the BCFW recursion. And here you can see that there's actually no integral reductions, no algebraic reductions at all. Because we did them once for all, and in fact, we didn't do them explicitly. We argued what the result of them should be. Because they're in terms of on-shell tree amplitudes, they're manifestly gauge invariant. And as promised, each of the coefficients, at least for the boxes, is gauge invariant. And the other thing is that, again, something I didn't emphasize for the BCFW is that you can actually implement them purely numerically. You don't have to write down an analytic formula. As it turns out, the BCFW recursion is not the most efficient for numerical purposes, but I'm not going to have time, I don't think, in this series to explain that statement further. Here, again, you can, assuming you have some tool, be it BCFW or something else, for evaluating tree amplitudes, then you can evaluate this purely numerically without ever having to write down a formula. So it's suitable for direct numerical implementation. And today, for a change, I will stop on time, although that's cheating by not doing the last 15 minutes of today's planned lecture. Are there any questions? Yes. Why don't you use a microphone? Oh. This one is out of battery, I think.
For 4 dimensions, we can directly say that we cannot cut simultaneously more than 4 propagators, right? So can we argue that as we cannot cut more than 4 propagators simultaneously, we cannot have diagrams with 5 gons or 6 gons, something like that?
Well, that's a little bit tricky because the loop momentum is actually d-dimensional. So I didn't demonstrate this to you explicitly, that one can actually do the cutting in 4 dimensions. That's actually a special property at one loop. It's not generically true at higher loops. So, but yeah, the argumentation about reducing to a set of integrals relying on the 4-dimensionality of the external momenta, that does carry on to higher loops.
Yeah, like for one loop, we can argue that for. Can we argue that for?
Can you speak up a little bit?
Yeah, for one loop, can we argue that for? Let's say we are in d dimensions, then for one loop, we will start with d gons and then we'll go to d minus 1 gons and d minus 2 gons and so on.
Yes.
Can we do? Okay. And can you please explain that line to me? I missed it. 2 problems cancel out each other.
So there are analogous statements to this at higher loops, although this style of doing generalized unitarity has not really fully been worked out at higher loops. I'm not going to talk about it, but in addition to working at the level of integrals, one can also work at the level of integrands. And that's the technique which has been worked out at higher loops. So, and then it's not that the problem cancels itself, the problems cancel each other out. You have to take into account the analog of that statement at higher loops. Okay, I think everyone is probably tired, so if you have any questions that you forgot to ask today, you can ask them tomorrow, because I will do an example tomorrow, and then if I don't remember to stop right afterwards and ask for questions about today, then someone please remind me.